Welcome to this session with a special focus on automotive. Our first speaker is Franck Bernard. He holds an engineer degree from Grenoble INP and a Master of Science from Telecom Paris. He started his career in 1990 as a researcher in medical imaging, and then he occupied several positions in 3G and 4G technologies at Philips, NXP, and ST Ericsson. In 2012, he was hired by ST Microelectronics to manage the development of smart rear camera ICs. And in 2015, he joined Bosch Automotive Electronics, where he's deputy manager of the EIY group, which develops digital IPs and system on chips for the automotive business.
Thank you, Jérôme. Can everybody hear me? Yes. So let's try whether the next works. Fantastic. It works without me pushing it. So thank you for listening. My first question would be, how many of you guys know about Bosch? Who knows Bosch? Great. That was my next question. My next question is, how many know Bosch as an automotive supplier? Less, but it's still a lot. And how many know Bosch as an IP and an IC supplier? Even less. Yes, I'm happy that you say that. We are not only windscreen wipers makers and refrigerator makers, which is an important asset for us, but Bosch as a whole is a 90 billion euros company, turnover company this year, out of which 2/3 is manned by the mobility company. And the mobility company is about everything that moves, from electric bike to lorry and of course to cars. And the point I want to make here is that we often think that we are only tier one. That means assembly supplier also making chips. And I will focus in my presentation on the need from the Bosch Automotive Electronics, so namely the guys who are making chips and possibly IPs from RISC-V and from other vendors. Okay, my talk would be about presenting what we intend to do in the next coming year, what are our challenges, how we map these challenges to requirements, and how we foresee that RISC-V can be one solution to those requirements, and of course giving a little bit of conclusion and perspective at the later stage. First point I would like to introduce is I will not give you a solution-oriented presentation. I will give you a problem-oriented presentation. Until today, I've seen many people coming with solutions. I will come with my problems. And I will help that all the ecosystem will help me solving it. So today we start with the high-level picture at Bosch. We are at the heart of a 3 major transition period, and they happen unfortunately at the same time. So we have to go towards software-defined vehicle, we have to go to electrification, we have to go to autonomous driving. Yes, you see them. Software-defined vehicle, for us, that means that the primary design principle shifts from hardware, I don't speak about mechanics, but from hardware to software. Electrification calls for a change from our natural sweet spot, which was the combustion engine, to electric motors. And autonomous driving calls for the change from a human control behavior to a machine control behavior. In addition to those 3 transitions, you need to understand that it changed also all the business models to us. We have prescriptions from OEM to tier 2, to tier 3. We have tier 1 changing their behavior. And all of this let's say, accompanying the change that we have more and more end-user interactions. When I say software-defined vehicle, you can also think about more and more software functions, more and more added value from the software. And it starts from day one. As soon as you have a car sold, you can be offered possible services. And all of this is about where I'm going to try to give you a journey to and help you understand. I mean, I try to let you understand what are headaches these days and try to get some support from you guys. So let's go further. When we discuss about these three major changes, we discuss about a change that affects not only the overall, let's say, representation of the function and the allocation, but also from the way we are challenging the set of, let's say, components to software stack. So grossly, when we discuss about software-defined vehicle, I said that we started to change from a primary, let's say, hardware design principle to a software design principle. That means that we're going to have to think differently. We're going to have to think with the capability to take into account that the software guys have an enormous amount of effort to spend to finalize the car or the subsystem in which they work, and that the hardware needs to accompany them. But you do not have exactly the same challenge in all pieces of the electronic components that make a car. And in addition to the software-defined vehicle trend, in fact, we have to accompany them, and we accompany them, those changes, I mean, with a change of the end-to-end architecture or the electric and electronic architecture. So we changed from something which was initially and still today in majority a distributed architecture, where grossly you have every single function assigned locally with, if possible, a direct activity on its sensor activator. So you have, until these days, something like 100 ECUs in charge of a dedicated function in a car, and you change from that to something which is more either domain-centralized or vehicle-centralized. That means that we accompany the change by trying to have a couple of pieces which are enabling a smarter architecture and a leaner architecture. When I say about software-defined vehicle, you need to think that there is a fundamental paradigm which is to try to put software as a function anywhere in the car. Of course, that doesn't work exactly the same thing, that way. But the fundamental idea is that you would try to be able to enrich and assign functionality in a quite opportunistic way. To do that, you will keep still your sensor actuators as the heart of the local, let's say, activity to control and perform things that can be done locally. So sensor actuators, that means edge device that can be a radar, that can be a LiDAR, that can be a braking system, that can be a door opener, everything which can be treated locally. Between that and the central vehicle, where you're going to have all the brain activity, you can have domain-centralized stuff. That means, for example, that you can have direct connections between a LiDAR and an ADAS system. You can have a direct connection between, let's say, vehicle motion integration platform and all the activity or the actuator and the sensors that are linked to it. So there is a gradation that can be afforded a long time, but also in terms of space, and we will not see something which is absolutely the ultimate trend that can be, you know, like a big vehicle, a central vehicle, and with dumb gateways transferring all the data to these big brains and with very dumb actuators and sensors. We'll have something that will be a change which will adapt to local processing, zone controllers, where we're going to have not only the I/O going there and acting, if you want, like a service to, we call that signal to service interface between the sensors and actuators and the vehicle computers. We're going to have also some application control level in the zone controller. So that's the change that we have these days to face, and that gives you a little bit the environment in which we speak. So going one step further in details, we, Bosch, we are doing sensors and actuators. We are doing dumb sensors and smart sensors. We are doing zone controllers. We are doing zone controller chips, namely accompanying the data, but also maybe locally some controls, such as, for example, the idea to have integration of dedicated hardware functionality in the zone that will handle body or climate stuff, or locally, window control on the left seat zone, for example. You're going to have gateways which will have to accommodate a huge amount, an increasing amount of data traffic. So we don't speak anymore about only CAN transferring information at 10 megabits. We speak about 100 megabits, 1 gigabits, and maybe later on 10 gigabits interface to accommodate raw data output from images and radars. And we speak about things that are at the vehicle computer able to take into account a very large amount of information and be able to support very demanding CPU demands, but not only CPU demands, also graphic demands, also AI processing demands, and this kind of stuff. Out of this, you can feel that on the sensor and actuator, we have a low pace of update. When I was speaking about service and functions, I was thinking about things that generally happen on the vehicle computer. That means that everything which is tightly attached to safety and local control will be, of course, upgradable, but at a rate which has nothing to do with an upgrade of service and functions. The same thing acts for zone controllers, granted that the zone controller will have another layer of activity, which is to transition from this very specific activity handled by sensors and actuators up to the vehicle computer. So they will make this transition, as I said, and here you can expect to have more software updates, software upgrades, than on the sensor and actuator. On the vehicle computer, of course, not only you have to have something which is, I would say, as much as possible able to sustain this generic paradigm that I was depicting, so something which allows the software stack to be acting as relatively independent from the hardware. But you will have also to have specific hardware. When I say a software stack independent of the hardware, that doesn't mean it is totally agnostic. You need to have dedicated processing because we need to have something efficient. And you do not control exactly a generic scheduler like a neural processing IP. So that was my generic introduction. So if we start from this point of view, what we can see is that at a high level, we at Bosch, we can think that we would like to start trying to make ADAS chips which are able to take into account this change, and we will need something which is able to do autonomous driving, and try to think whether we can also accommodate something more than pure autonomous driving, and we think especially about IVI, infotainment vehicle. So this central vehicle, it receives all of the information from inside the car, but also from outside, so you have to deal with the connectivity items here. So we need to re-architect our ADAS setup with the idea to have something affordable, scalable, being able to adapt to the complexity, though flexible. And as you know, the amount of cars expect to be ranging up to in the range of something in the 100 million equipment a year, I mean cars a year. But to sustain the amount of performance required, it is in log on the left, under computer performance. You need to think that it costs an enormous amount of money in terms of hardware, but also in software. So, of course, the more demanding the autonomous level, the more demanding the tops. And the more demanding the tops, the more demanding is the CMOS node. We need to put the right CMOS node in operation to face this amount of tops. So when I discuss about tops here, I mix voluntarily the control processing and the AI processing. To sustain that, we will have to take into account another paradigm, which is the ability to take into account the fact that we will not be able to only do SoC, but also to have to cope with chiplets. So chiplet, I will not come back again what was discussed this morning with our colleagues from Ventana. The idea is that you cannot always afford a dedicated SoC to sustain the range, the rate of changes, the rate of flexibility, because the cost of SoC is bigger and bigger. That's the first point. The second one is that you need to go down and down in CMOS node, and as you know, if you put some analog stuff, analog doesn't shrink, so you waste a couple of square millimeters. And in addition, as I guess you know, with the defect density, the larger you are, the less yield you have, and it also increases the cost. So we need to think about the chiplet-based systems. And here, grossly, the idea is that we're going to have chip dedicated for standard CPU processing, chip dedicated for GPU, chip dedicated for AI in general. And actually, we are actually working on a smart architecture that is able to support this chiplet-based systems. That means something which is able to scope from the level 2 autonomous driving capability up to the level 4, not to speak about level 5. So we need to find the right granularity with all of these building elements. So we need to find the right grammar, in other words. And because we have also some geometric constraints, we need also to find not only the functional grammar, in the sense that we need to assign a certain amount of, let's say, function into a certain chips, but also from a geometric point of view, to be sure that we can interface those chips together. So we will call, in other ways, to people, and here I'm expecting that some of you here will be able to support us in that chain, to have CPUs, but also GPUs able to support this change. And here we call for chiplets, not only for IPs. As I said, we need to support a certain scalability. And the scalability, for us, that calls for that way. So I focus here on the pure RISC-V between bracket capability. So let's say CPU standard processing. I exclude voluntarily the AI processing and the GPU processing. And here I just wanted to show that we have to think even at that level between things that will require something like 500 kilodemips, which is already big, up to 1,600, depending whether we want to go from level 2 or for level 4 autonomous capability, and to take into account that you need also to sustain a low end between bracket IVI capability up to a higher end level capability. So our challenge is that we will need to have chiplets that are adapting to that kind of demands, which is pretty demanding. We as Bosch, we don't intend to, let's say, fabricate those chiplets. We intend to sustain an environment that will enable us to perform a chiplet. Sorry, to perform a chiplet-based systems. So for this, we need 64-bit processors. We need something in the range of 10 DMIPS per megahertz. We need a large multi-core cache current architecture, heavily multi-threaded capability, whatever you want, with CMOS technology below 5 nano. That's grossly one paradigm in which we're going to work. And RISC-V for us is an opportunity to have more and more people sustaining this capability, I would say. Then, when we work at our level at Bosch Automotive Electronics, we work in a range which is totally different. So I was speaking here about those big central computer. We have also additional chips everywhere. We have chips at engine management, we have chips at brake control, we have chips at airbag and safety, let's say safety restraints items. We have chips for ADAS sensors, we are building chips for radars, we are building chips for ultrasound systems. We are also doing PMIC, because as you guess, the power consumption and power management is a key point, especially with the electric change. We need e-drive control, and we do also have in-vehicle network chips that consist both of IP and chips. And in addition to that, we have also a couple of IPs related to computer vision, to gateways. We call it Enhanced Data Engine, EDE, and GTM, which is more an I/O aggregator or supporting also an engine management. So on this, we'll speak about things which are either locally assigned in terms of domain, so that's let's say the actuator and sensors, or in the gateways. So whether you think about smart or dumb sensors, whether you speak about IPs embedding itself a certain complexity in terms of scheduling processing, whether you go to a domain and whether you put in some domains the capability to handle data, you range with this kind of range. Sorry, you come with this kind of range. Something which is very lightweight in the range of 50, 60 dMIPS, up to something which will call for 16 dMIPS. So kilodMIPS, sorry. So you see here, we do not speak anymore about 1,000 kilodMIPS. We speak something between 50, 60, and 15K. But it still called for a certain range. In terms of TOPS, so again, signal processing and AI processing, we have dedicated neural network IPs, so that range in the range of 400 teraportion per second, but we have also dedicated processing in smart sensors, just as, for example, the radars. And whether we are low and high on that, there is no more change. So here we're going to call for 32 barrier chips with excellent real-time capability, with some performance of, reasonable performance, but not tremendous, something between 2 and 3 dMIPS per megahertz. We speak about some SIMD capability, FPU as options. We need also to have some customization in our core, so either as tightly attached processor or as, let's say, modified pipeline stuff to accommodate our own flavor of functions. We need to speak about a technology that can range between 60, 65, down to 60, maybe lower, something in the range of 10 nanometer for CMOS. But in the range with, let's say, something which will, for a single core, can go up to 1 kilodMIPS, and with system for, especially for zone controller, that can accommodate 2 or quad core. What do we seek now from RISC-V? So RISC-V for us, it has a big chance. As I said, I want to discuss about opportunities and not solutions. So we expect from RISC-V this vendor independence. We expect this geographic independence. And from these 2 points, we expect grossly to sell our chips everywhere without any constraints, and also to benefit from cost competition. We expect to work with some open source IPs. We'll not have a single fit-all solutions in our view for the time being. The important point is for us to have something where we can have lasting relationship. We are an automotive business, so it's not for 1 year, it's for 15 years that we are engaged together, even more. We need to rely on an ecosystem which is performing and long-lasting. And open source for us is very important because it means that we can rely on more than one vendor and something which is continuously upgrading. We expect also to be opportunistically able to customize the ISA, maybe up to the capability of extending to some specific data handling, and to have a very good and dynamics in the ecosystem. I should say that what I've seen today was really, let's say, refreshing for me and re-energizing. I've seen many innovations, so that's really great. And I think it's also all those key points that make for us the RISC-V something specific of specific importance. We today, however, are just in our learning phase. So I speak here for our colleagues from Germany and for ourselves. So in Germany, we have people working in the scale for edge. These days, we are working with Tristan. So we are in our learning stage. So we have a specific focus on Sophia Antopolis on the CVSX extension. And as you can guess, with Bosch, we have the functional safety expertise on the hat. So we're going to support that. We are also trying to work with the colleagues on the open hardware group. I think we are in our own walk down to understanding more in depth this richness of this open instruction set architecture and the open source hardware. We have also specific points about modeling. Modeling is key for us, not only for verification, but also from the end-to-end modeling point of view, performance. That's also accompanying for us the shift left move that was also depicted this morning. That's also when you say that you have software-defined vehicles putting software ahead, you need to think that the guys need to put some software ahead of the hardware, or at least at the same time, so modeling is key. We are also in discussion with many RISC-V suppliers, matching our automotive needs. And as a whole, we can say that we are in an assessment phase. The idea for us is that we're going to put something in production in the years 2028 and after. We are making our mind at Bosch what we're going to do in this RISC-V industry, how far we're going to go, and with whom we're going to go. I will go fast on that. What is important for us? So we have the RISC-V engine, and on the RISC-V engine, we know what ISA has defined. We know what kind of flexibility it can give. So we expect to have a core which is achieving a certain maturity, which is yet an open point for certain items. And we want to be able to play with some customization, either, as I call it, tightly attached. So that means either, for example, with the open core with the CVX interface, or directly embedded into the pipeline of execution, or I would say, or let's say, not only tightly attached, but loosely attached. So we have a range of ideas how we would like to customize the stuff from a RISC core point of view, and what we want to put aside. Here we can do that from a generic point of view, such as an FPU, or from a specific point of view. When I say specific, I can put some safety ideas in mind, but I can also put some neural network things in mind and some specific automotive stuff. What we have seen is that in addition to that, which is mostly driven by the RISC-V instantiation of the ISA, you have a lot of additional goodies, which is also sustained by the RISC-V. So something like a second level RQ, something like core IPs, standard NOC interface, layer 1 cache, level 2 cache, etc., etc. And at system level, you can accompany that with system trace, DMAs, and anything which can be helping you to be more generic and customized. From a software stack, I didn't put anything specific to automotive because, to be honest, this we know how to make it, so I don't expect this to be brought by the RISC-V ecosystem. But at least what we would like to have is something which at least calls for TIS porting and a couple of optimized libraries, like some of the well-known vendors in terms of RISC are able to do. In addition to do that, I think we need tools for hardware development, so we need models and models that can be integrated into platforms. That seems something very important for us. We need, of course, VHDL and RTL to be able to play with that. Verilog for some of you. We need to put them in FPGA. We need to be able to customize them. We would like also to have something which would be more demanding, like an IDE, and if possible, to have a generic interface to handle that, to be able to customize the instruction pipeline, and to put our own coprocessor in it. We need a hardware safety package. If you want to sell us something, think that we are making something in safety. And in terms of software development, we need to have, of course, proven compiler and linker. We need tracer, we need debugger, and we need an instruction set simulator to be able to perform early development. I will not go into the details of that. What I mean is that out of all of this, we have defined a range of important items that can be ISA level, let's say, non-core pure functions level, such as hypervisor, FPU, SIMD operations, extension. What is important to know is that we need this range, and I think that this range will only come with a pipeline length of between 2 and 8 stages. We need low power design. All of this embedded stuff need low power. So we need clock gating, we need granularity in cache management, we need all of that. We need a hardware ecosystem that works well. So automotive compliance is key for us. So if you want to sell us IPs, especially hard IPs, think about the automotive compliance. There are things which are not automotive proven. We need layer 1 cache of good performance. We need efficient IRQ. We need monitoring IPs. We need trace and debug for instruction, but also for data. We have multi-core. We need multi-port capabilities. We need advanced memory management. We need standard interconnect interface. We still expect to use at least our standard interface. We are integrators, and we don't want to change everything at the same time, so we expect a compliance to XI4, XI5. We need DMA, and we need this idea that I was just depicting before. In terms of software, we need a performing compiler, C, C++, maybe Rust as well, but also safety compliant IPs of the kind. That means that we need to have a C, C++ compiler which is ISO 26262 ISA certified to make it automotive proven. We need optimized library. We need model, and this model, as I stressed before, needs to be coming from IP to the virtual SOC to the virtual ECU. So we need a chain that enables that. We need debugger, profiler, tracing toolsuit, and RTOS. Last point is about the functional safety attributes. We all know about functional safety, but I need to stress one point. Functional safety starts with a efficient, mature design capability. So it's not about only, these technical measures putting things to avoid or to cope with transient and permanent faults. That means that it should be at the core of the development process. Grossly, it's not because you put twice the same thing in parallel that you execute twice the same thing like in a dual core lockstep that it makes it better if there is a fundamental flaw in your initial design. So we need something that is absolutely mature, and it should be developed according to a mature and safe development plan, otherwise called the ISO 26262 SLD capability. We need a safety package. That means we need FMEA, we need DFA, we need to be able to integrate your IPs into our systems. And you need to think about that first. You need to, when we start in an automotive design, we need to know about what impacts a failure can have, so that the guy who integrates that knows about it and can take actions, or can tell you, no, that doesn't work, I will not be able to cope with that. I will not, let's say, depict all of the physical stuff that can be, let's say, required, but you name them, so protection and physical data, protection and control data, duplication. So think also about the fact, as I said, that hardware is important, but software as well. So safety package also concerns software. In security, again, I will not go into it. Think always, there was an interesting question, think always that when you make something safe, often you have make it secure. That's not totally true. But you have also the same, if you make something DCLS, for example, it is by nature able to capture an issue when one of the two cores has been attacked. So if you shift that in time, and physically, it will be difficult to attack the same thing at the same time and result that in something which will be invisible. In general, we think in safety and security more at the system level. So don't try to put every single goodies inside the IC. We need to think system, and we can help you there. In conclusions, what I would say is that what I've witnessed with the colleagues in Germany is that today we have already ASIL-D-capable IPs, which is for us a very good sign that RISC-V can definitely enter the automotive industry. We need still to make sure that all of these C++ compilers are ASIL-D capable, but I think we're on the right trend. And again, I was very impressed this morning, and I was happy to attend this session today. That's the first time for me and for some of my colleagues. The ecosystem is progressing well and fast. That's critically important, and I think it's a very good sign for us. Our next target is to be able to be provided with cycle approximate and flexible instruction accurate models, though flexible. That means that they are able to be integrated into mature virtual platform creators. We need to also have trace and debug ecosystem pretty mature, and PPA of competition in the range that I was speaking. And for us, the challenge that I just tried to depict is we see we are entering this open hardware group that's tremendously dynamic, so we need to accompany them. We need to take into account that it takes time to mature the ecosystem with that many actors. And we see good signs on the verification improvements, but we know that we need to put some effort on it, especially from a functional safety point of view, but that's good. And the last point that I had in mind, and I know that Mark already explained this morning that you guys at RISC-V, you have already this idea, but we were speaking about CPU, but why not about GPU? So this in a nutshell, what I wanted to show you. So it's a call for support for us, more than a set of solutions. And I thank you for your attention.